And we're live. So we're going to do something a little bit differently today. We're going to do, this is actually a live lecture. Say hi, class. I don't know if you can hear that on the mic or not, but this is a chemistry class, September 26th, 2012. I'm going to show you what I show them. So today we're going to use what we call a PhET simulation. So the first thing that you can do if you want to do this at home, you can actually do this. Go to any kind of search bar and type PhET, P-H-E-T. That PhET stands for Physics Education Technology. And click on that first link, phet.colorado.edu, and that's going to take you to this site. You click on Play with Sims, and this is a bunch of simulations, and anybody can do these. They're free. I'm going to click on the chemistry link, and you'll see a whole bunch of chemistry simulations here. I'm going to scroll down. The one that I'm interested in today is the nuclear fission one, or if you prefer, the nuclear fission if you like to sound wrong. So I'm going to, you can either download it and have it on your computer forever, or you can just click Run Now. I'll just click Run Now and open with. You'll need Java installed on your computer, but that's also free. And it takes a few seconds for it to start up. Actually, while that's starting up, though, I'm going to go back in here and I'm going to start up another one that I know that I'm going to want here in a second. And woo! Woo! There we go. I'm going to go back to... it started up now, but I'm going to also open up the beta particle, the beta decay one. So we'll have that open and we can go to that if we need to. And run now. And open with. There we go. So while that's opening up, I'll show you what we've opened. This is the simulation that we've opened up. Excuse me. You can see that we have a nucleus, uranium-235, and this is relatively stable. This nucleus is relatively stable. It is, if we just sit and wait for it, you know, in the past examples we talked about alpha particles and beta particles, they would just kind of spontaneously decay. They would not be stable and they would break apart. This guy, if we just sit and wait for it to decay, it's not going to. It's not going to decay. It's relatively stable. It might take a few million years for it to break apart. If we compare that to our beta example, let's take out of our old bucket of atoms here and let's add a bunch of hydrogen-3 nuclei, and you see that what they're doing. They are kind of hanging out, wiggling around. Oh, boom, I just shot something out. And still just hanging. Oh, boom, just shot it. Oh, boom, ah! And every once in a while they just notice that it's kind of, can you tell which one's going to happen next? How? By direction? Well, I don't think you can really tell that which one's going to go next. If you can tell which shell, tell me which. You can't. It's actually a random process. There is no way to tell which one's going to go off next. It's completely spontaneous. It happens for no particular reason. You in the back. The question was asked, what if they hit each other? Are you asking about the little blue balls that are flying off, if those hit each other? I believe if we reset it and watch it again, you'll see that if we had a bunch more in here, the blue balls will hit things and that will have no effect. See, it'll just kind of go right through them. You see that? See, there's one that just hit and nothing happened. So it's not, when those blue balls, if you look up here at the top right, those, that is an electron. That blue ball represents an electron. And the little green things are antineutrinos. We do not want to talk about antineutrinos today. But so this is what we did yesterday. This is beta particle production. You're just kind of watching these. When does it happen? Whenever it wants, kind of spontaneously. Now compare that to the video that we are looking at over here. If you had a whole bunch of uranium-235 nuclei, and we can get a whole bunch if we like, we can go have as many as we want, and we can just sit and wait. Alright? Which one's going to go first? Well, none of them are going to go first. They're just going to sit there. Okay? But if we go back to our previous example here, I have a gun. And this turns out to be a neutron gun. I can shoot neutrons at this nucleus. And something amazing happens if we do that. Are you ready? Are you ready? They're not answering me. Yes, they're ready. Okay, there we go. And boom, oh, here comes a neutron. You see that neutron? Oh, it's stuck. Oh my gosh, I'm freaking out. Oh, I'm orange for some reason. I'm freaking out. Oh, no, no, no. That wasn't good. That wasn't good. Look what you did to me. That's what it's saying to us right now. It didn't like that. It was stable, and then we shot it with a neutron, put an extra neutron in there, and all of a sudden it's not happy anymore. It's not stable, and it breaks apart into bunch of things. We'll talk about what they break up to into in a moment, but that's the basic point, is that had we done nothing to this, what would have happened? Nothing, because it does not undergo a spontaneous decay process, at least not very often. But if we bombard it with something, in this case with a neutron, we can cause it to become unstable, because there's a certain ratio of proton to neutron that it likes, and if it gets off of that ratio, if you give it too many of these or too few of those or something like that, it's unstable and it breaks apart. And so that's what we're going to do today, is we're going to talk about how one, what time have we got, by the way? I got somebody timing me because I know I have to keep this under 15 minutes. So just give me a finger sign when we get to different numbers. And so what I want to do now is I want to kind of, if we watch this just one last time, I'll actually pause it. And if we pause it right here, what do we have? We have a neutron, and we have a U-235 atom. So this thing right here, that thing right there, that is a neutron. So we can write the symbol for a neutron. This is before they collide. Remember that a neutron has a mass of 1 and an atomic number of 0. In this simulation, it's pretty good because you can see the masses is basically how many of those little balls, how many spheres it has. So that has 1 sphere, and the atomic number is how many of them are red, because the red ones are protons. So it has, that guy has 1 sphere, none of which are red. So we write 1, 0, that's a neutron. And this guy over here, he has 235 spheres, and if we actually sat and counted them, we couldn't. That would, I don't think it shows all of them, but we can tell from the periodic table that uranium would have 92 reds. And so that's what we're starting with. This is before. Notice this is different from the spontaneous reactions that we did before, because in the spontaneous reactions we did before, you didn't have more than one thing on the left. You have here, this thing is not going to do anything unless we add something to it. Before we would just say, well, something starts out and then becomes something else. And so that is what we're going to start with. Now, what does it end with? Well, that's what we want to do next. So I'm going to go ahead and clear that layer, and I'm going to let it play out. And there it is. It's unstable. It's got that extra neutron, and then it's going to change. It's going to break apart, and boom, there it goes. And I'll pause it there. Now what do we have? Well, we have 3 of the gray things. And so let's go back to what we had before. I had to clear it off whenever I showed the movie, but we started with a neutron, and we started with 23592 uranium. That's what we started with. That was before. That was before we did anything to it. But now that's not what we have anymore, is it? We don't have that. Now we have not 2 particles, but how many different particles do we have here? 5, somebody said. Is that true? That's 1, that's 2, that's 3, that's 4. 5 different things. That I would agree with. We have 5 things now instead of 2. And so our in our reaction, then we got to show what those things are. And so this is what the homework is going to be like tonight. It's going to say things like, you start by bombarding a uranium-235 nucleus with a neutron, and then it'll tell you some of the things that are made, and you'll have to figure out what the other things are. So let's do that here. So I'm going to tell you just from the picture. There's certain things we can tell from the picture. What's something that we can tell from the picture is given off? What? Neutrons, he said, and he was correct. We have how many neutrons? 3 neutrons, he said, and he is correct. So the way we show 3 neutrons, we don't put a 3 up there. It's not like there are 3. It's not like it has a mass number of 3. It still has a mass number of 1. There's just one of them. But there are 3 separate instances of that, correct? So we have it 3 times. We have a neutron 3 times. The way we show that is with a coefficient of 3 in front of the neutron symbol to show that there are 3 of them. Now there's got to be 2 other things here, and there's frankly no way you can know what those are unless I tell you what one of them is. So I'm going to tell you that this guy right here, in your homework it would say like 3 neutrons are given off, and a, let's say that this is krypton 101. Okay, so that would be given to you in the problem. There's no way for you to know that that's what it was. You'd be told that that's krypton 101, so you would add that to your product side, and you have 101. Krypton is 36. We can get that from the periodic table. Okay? So the problem would say something like this. Uranium-235 is bombarded with a neutron, makes 3 neutrons and krypton 101, and one other thing. One other thing. Now, what is that other thing? We actually can figure that out. We can figure that out in the same way that we figured out what the product was in a beta decay or an alpha decay. And do you remember what that is? Remember what we look at? Pardon? Don't look at the electrons, because this process doesn't have an electron given off. There are no electrons here. What we're going to look at is these numbers. Remember the gray balls and the red balls. The gray spheres and the red spheres. Don't we have the same number now as we did before? Did any of them go away? None of them went away, so they're all still there. So what we can do is we can say, well, before we had 236 spheres, right? So now we should have still 236 spheres. So how many have we already accounted for in our reaction? 101 here, and then 3 more here, right? We got 3 ones. So that's 104. So we started with 235 plus 1 is 236, and we've already taken care of 104 of them, which means that we have 132. Am I doing my math right? 132 left. So in other words, this thing must have how many spheres in it? This thing must have 132 spheres in it. And how many of them must be red? How many of them must be protons? Well, we look at the bottom here. We started with none here. Started with none here, 92 here. So we should have, after the arrow, there should be 92, right? We need 92 after the arrow. How many do we already have? 36. So how do we find how many more we need? We subtract 36 from 92. For a total of 56. So the bottom number here of the thing we're making is 56, and the top number is 132, and that would be what? What has an atomic number of 56? Barium. And that is our nuclear equation for the bombardment of uranium-235 with a neutron. It's a lot more complicated than what we did before, but the basics are still the same. The numbers on the bottom before the arrow have to add up to the same as the numbers on the bottom after the arrow, keeping into account that you might have to triple them if you have a coefficient, and the same on the top. Numbers on the top before the arrow have to add up to the same as the numbers on the top before and after the arrow. And that is the end.